Okay, now let's attempt to do problem 433. So I have it there at the bottom, so I'll just read it. A randomly pollinated strain of mice produced ears that are 24 centimeters long on average. After one generation of self-fertilization, the ear length is reduced to 20 centimeters. Predict the ear length if self-fertilization is continued for one more generation. So for this problem, the one thing to remember is that in lecture, we mentioned that when an organism selfs, then the inbreeding coefficient for that next generation is 1/2. Um, After we do that, you also sort of have to remember that in an outbred population where there's no inbreeding going on, the inbreeding coefficient is 0. And so here, in this, I have to write it all out at the first to do these videos. So um, I'm just going to point you through each of these. And so here we have an inbreeding coefficient of 0. This is in the F column, and I put this over 4 just so that we can see the pattern a little bit later. And then the length of the corn was 24 centimeters. So when there's no inbreeding going on, there's the length is 24 centimeters. When there is selfing going on, or when there is an inbreeding coefficient here of 1/2, you have a reduction of the total length of the corn by 4 centimeters, and so you get 20 centimeters. So again, here now you have paired XY data, 0, 24, and if we do it over 4, we would say 2 paired with 20. And so now we have to figure out, okay, in the next generation, what is the inbreeding coefficient going to be? And so if you have another round of selfing, again, the inbreeding coefficient would be 1/2, but now the second generation, so if you can't see that, that is F of 2G, is the product of an individual that also had selfed. And so here now you have to go to that equation for the inbreeding coefficient of a common ancestor, because F of G2 is the product of an inbred ancestor, which was the organism that was selfing in the previous generation. So if you remember, that total inbreeding coefficient, the F of 2G here, second generation, that's the 2G, is equal to the F if the organism, or if the common ancestor was not inbred, times, and this is the equation from the lecture, 1 plus the inbreeding coefficient of the common ancestor. So we know the inbreeding coefficient of the common ancestor, right? The previous generation, that was 1/2, right? And the inbreeding coefficient, if there was no inbred ancestor, would also be 1/2, because by definition, the selfing is 1/2. So you just substitute in here 1/2 times 1 plus 1/2. Solve for that, that equals 3/4. So the inbreeding coefficient now of the next generation would be 3/4. And so what we have to figure out is how much now will it be decreased, because we've increased the inbreeding coefficient. As you can see, we kind of skipped over what an inbreeding coefficient of a fourth would be, but just to show you the pattern, I'll put in the 1/4 here. So here's an inbreeding coefficient of 1/4. If it dropped from 24 to 20 in 2/4, in 1/4, it would have dropped from 24 to 20. Therefore, if you add another 1/4 to the inbreeding coefficient, going from 2/4 to 3/4, the total size of the corn would then drop again 2 centimeters to 1/8, or to 18. And so 18 centimeters is your answer. You can also do it using an equation. And so here we have our paired data, 0, 24, 2, 20. And with that, you can calculate a slope. 24 minus 20, 0 minus 2 equals -2. That's your slope. Put it into that equation. Y equals -2x plus the y-intercept, where x here is 0, y is equal to 24. Now you just substitute that 3 in there. 3 times -2 plus 24 equals 18. So those are both just two separate ways in how you can solve that. If you want to just kind of look for the pattern, you can do that. If the pattern isn't really apparent, right, like doing it the way we did it up top there, then it maybe would be better to use the equation. But you can do it either way, whichever way whichever way makes the most sense to you.